So one more short video to finish up with chapter 21 in physics. And this has to do with something called capacitance. So this is section 21.2, and it deals with capacitance. The word capacitance, as you can imagine, comes from our word capacity, which means to hold. Capacity, which means to hold. Early on, they realized that they were going to have to find a way to, if they're going to work with electricity, at times to hold electricity. And there's a way to do that. Now, I want to review something that's in the book, and that is that if I have, say, a sphere, and I put charges on it, especially if it's a hollow sphere, those charges will move as far away from each other as they can. The reason is because of Coulomb's law that those charges, if those were negative charges, they would move just as far apart. The charges are trying to get as far away from each other as possible, and the easiest way is to distribute on the outside. If I bring another sphere to here, close to here, if there's a way for these charges to get pushed off and jump across, they will. If I connect this with a wire, then half of the charges, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, half of these will move over here, unless this is smaller. So if I have but this is much, much tinier, well, then I may only lose a couple of the charges so that the distance between these would be the same. So that these will now spread out and end up being roughly the same distance as this one is. And that's called grounding. So we're always going to have that situation. Now, what happens with a capacitor is that we're going to have, usually with a capacitor, they take two metal plates and they take and they start adding charges, basically, and we can think about it as making one side positive, take away charges from one side, add charges to the other side. These create an electric field, which means that there is a voltage between there, and that voltage is going to depend upon how many charges there would be on here. But because this is an insulator between here, just like here, once the charges get on, they can't go anywhere. Now, if I was to take and put a wire from here to here, this will discharge, and it will immediately take the electrons from one side and bring it to the other. If you guys had been in class, we would have taken, and I would have filled up a capacitor and we would have used U. We send the shock through you. Some of you have seen that done before, but I have a capacitor that holds charge, and we have everybody hold hands and we touch it and it shocks, but of course we can't do that over a virtual classroom. So think in terms of there being a voltage between here, because there is an electric field and there's some distance. Most capacitors are like industrial capacitors. You buy a radio, you buy a electronic device, there'll be capacitors, and the capacitors are usually just two pieces of aluminum foil separated by a insulator of some sort, a piece of plastic, and then you can put charges on here. The charges, the equation for a capacitor is actually relatively simple. A capacitor's equation is that the capacitance is the charge divided by the voltage. In other words, put some charges on here, the voltage will go up, but this remains a fixed ratio. So our equation would actually be C, and I know that looks like coulombs, but Q over V, and actually delta V as we start raising the voltage. All right. The unit of capacitance is the farad. Capacitance is the farad. And as you can imagine, that is named after Michael Faraday himself. And 1 farad means that we have 1 coulomb with whenever we have 1 more coulomb with every 1 volt. So 1 farad is 1 coulomb per volt. By the way, 1 coulomb is an enormous amount of electricity. You may remember the problem we talked about how many coulombs in a lightning strike, and it was 25 coulombs. If you have a 1 farad capacitor, like my friend who was an electrician used to say, that is a loaded weapon if it was charged up. So we're not going to ever use anything. In fact, more often than not, you will work with microfarads, picofarads. This is times 10 to the negative 6, times 10 to the negative 12, maybe a nanofarad, which is times 10 to the negative 9. So 1 microfarad, just for those of you who've forgotten your metric system, is 1 times 10 to the negative 6 farads. And the problems are relatively simple. What they will do is they will give you part of this information. They might say that, you know, we have a 50 microfarad capacitor, and we put across it 20 volts. What is the charge that's stored? It's real easy. It's not a difficult equation at all. C is Q divided by change in voltage. So Q is equal to C times the change in voltage. In this case, the change in voltage, you might say, why change in voltage? Because we started out with 0 or we started out with 10 and we went up to 30. It doesn't make any difference. So this would be 50 times 10 to the negative 6 coulombs times 20 volts. It would be 1,000 times 10 to the negative 6. And this then would be 1 times, moving that over, 1 times 10 to the negative 3 coulomb. So that would be 1 millicoulomb.